Okay, welcome to fourth lecture stability of structure. So, let us briefly recapitulate what we have done. So, we have introduced the concept of stability and we have also learned that how we can ascertain about the stability, nature of stability through the energy functional, and we have solved a simple problem, and thereafter we have considered four different kind of system, which is simple system consisting of a rigid bar with concentrated spring, right, concentrated elasticity. Restoring force are offered by this concentrated spring, either rotational spring or translational spring, right. And then we have seen that the stability behavior of all the structural system, elastic structural system, can be approximated by considering this apparently simple system. The first system we have considered a rigid bar restrained by a rotational spring, which is subjected to a concentrated load P, and we have seen that the system demonstrate symmetric bifurcation behavior and the post critical path is stable, right. So, a fundamental path, a stable fundamental path bifurcate into a unstable into a stable post critical path and a unstable fundamental path, right. And then we have shown that this kind of system which is showing this stable bifurcation also demonstrate, we have also investigated its imperfection sensitivity, and we have seen that it follows 2/3 power law of imperfection sensitivity, but it is not imperfection sensitive, meaning the critical load increases with increasing imperfection, okay, which is a hallmark of this kind of stable bifurcation, right. So, now we are going to consider, we have also seen in a previous example that the bifurcation is eliminated on incorporation of imperfections. So, bifurcation behavior is only noted when it is a perfect system, right. So, stable fundamental path is bifurcating, okay. Fundamental path means where the equilibrium is for theta is equal to 0. For non-zero value of theta, okay, this is the path which basically showing this is the path of bifurcation, right. But on incorporation of imperfections, the bifurcation ceases to exist, rather the stability behavior, the stable the equilibrium path asymptotically approaches the equilibrium path of the perfect system, that we have also demonstrated in the stability diagram. Now, we are going to consider the second category of system, which shows symmetric bifurcation, but an unstable post critical path, okay. So, the hallmark of second kind of system is symmetric bifurcation, with unstable post critical path. So, this system you may recall, we have all discussed about this twice system. So, this system is once again this is a rigid bar, and this rigid bar is pinned here, and then it is restrained by, so here it is restrained by spring of stiffness K, and this is P, and the length of this bar is L, okay. This bar is rigid. You see this support has to be roller, because it must allows the translation along the vertical plane, in its vertical plane, right. So, now the first lesson that we have learned in any stability analysis is we have to perturb the system, we have to look for alternate configuration. So, the system degree of freedom, this is a single degree of freedom system, because all the displacement here can be described essentially by rotation, right, because it is rigid. So, let us perturb it. So, this fellow will its locus will be alternate locus will be here, right, and then it will come down, and then maybe this spring goes like this, right. So, I am assuming this. Let us first study the perfect system, and then we will impart imperfection, right. So, this angle is theta, right. So, then load P is going there, and if it is L, so I am going to write down the potential energy function. So, potential energy is equal to strain energy minus work done. So, strain energy is what? What is the strain energy? Now, strain energy is contributed by this spring which is deformed, right, and what is this? So, what is the displacement between these 2 points? If this angle, this is L, then L sin theta, this one, right, L sin theta. So, you can write half K L half L square theta, half K L square sin square theta, right. So, the restoring force is K into L sin theta, right, is not it? And then, so that is half K L square sin square theta, right. So, minus, and then what is the work done? The work done is, so this point the vertical displacement is nothing but this is L and this is L cos theta. So, P into L 1 minus cosine of theta, right. Is that fine, right? So, let us first see the equilibrium path. So, let us first find out the equilibrium path. For equilibrium path, so a system need to be in equilibrium. For equilibrium, we must have the potential energy function minimum, right? Minimization of potential energy function del pi del theta. So, what we obtain is half K L square 2 sin theta cosine of theta minus P L is sin theta is equal to 0, right. So, P is K L square sin theta cos theta divided by L sin theta, and then this will go. So, K L cos theta, right. This is equilibrium path, right. And then we are also going to find out critical value. So, for that del 2 pi del theta 2 is equal to 0. So, del 2 pi del theta 2, we further differentiate, what we are going to get is K L square sin theta into minus sin theta, right, plus cos theta into cos theta means cos square theta, right, minus P L cos theta is equal to 0, right. And then it is K L square cos square theta minus sin square theta means cos 2 theta is equal to P L cos theta, or P is equal to K L cos 2 theta by cos theta, right. Fine. Now, okay, so let us keep the equilibrium path. So, here we will put this P equilibrium as K L cos theta, okay, and what we will do, we will substitute this equilibrium path on this condition, right. So, del 2 pi del theta 2. So, you see that here when theta tending to 0, right. So, what it will, P is equal to K L, right, for theta is equal to 0, right. So, that means P critical, it will be K into L, right, fine. When theta is equal to 0, that is what the critical load is, okay. And del 2 pi del theta 2 is will be nothing but K L square cos 2 theta minus P minus L cos theta, and P is nothing but K L cos theta, okay. So, here if you KL square cos 2 theta minus cos square theta, and this is nothing but minus KL square sin square theta, right. So, what we see, del 2 pi del theta 2 is always less than 0, right. So, that means it is always unstable. That means the for theta not is equal to 0, for theta not is equal to 0, that means for the any perturb configuration, that means the perturb configuration, it is always unstable. So, the post critical path is unstable, post critical path is unstable. So, that we understand. So, bifurcation will occur at critical load KL, right, and then it will lead to a stable post critical, unstable post critical path, right, clear. Now, what will happen at 42 pi d theta 2, please note that although I am writing partial, it is basically it can be total derivative because only one variable, right. So, this is minus k L square sin square theta. So, what about in the critical load? So, P critical is KL, right, and we want to check what is the state of equilibrium at. So, at the when it is just reaching the critical load, right. So, what is the stability at critical load, right, at critical load. So, if without investigating on the higher order derivative, if we take theta is equal to 0, then what is happening? Theta is 0, then del 2 pi del theta 2 is what? Is 0. That means it is indecisive. So, so you may comment, so that which implies that it is in neutral equilibrium, but that's not always correct. So, for that you have to investigate higher derivative. We see that is kind of confusing, that will lead to a wrong conclusion. Okay, so what will happen? You just differentiate it twice. So, you just del 3 pi d theta 3 is equal to 1 minus k L square 2 sin theta cos theta, right. That means minus 2 minus k L square sin 2 theta, right. Here also, if you take theta is equal to 0, it is 0, it is vanishing, it will not give any clue, right. Once again, I will differentiate it further. So, del 4 pi d theta 4, what is going to happen? Minus k L square 2 cos 2 theta. For what is this? For theta is equal to 0. If theta is equal to 0, it is minus 2 k L square less than 0. What does it mean? That means at critical load it is unstable. So, so that means at critical load this is unstable. You see, it is still unstable. So, whatever is we are unable to, so critical state is unstable. Critical state is unstable. So, if we try to check for the conclude the stability, try to conclude the stability from the second derivative, it is leading to a strong notion, right. So, you have to check for higher derivative, and we can see indeed like the post critical path is unstable. At the critical load, that equilibrium is also unstable, clear. So, you understand. So, a stable fundamental path bifurcate into an unstable critical path, right, post critical path, unstable critical path also as well as unstable post critical path, right, which is symmetric. Okay. So, now what will happen? So, we will just draw how does it look like. So, we have studied the system, the behavior of the system for the. Also, another thing I would like to note is that all of you have noted down things, right. Okay. So, what was the expression of phi? Phi is what? Half k L square Then what was the expression? Sin square theta minus PL1 minus cos theta. That was the expression, right? So, I just want to KL square by 2 sin square theta. If you theta minus theta cube by factorial 3 plus theta to the fifth by factorial, whatever, right? Highest we can always neglect PL 1 minus theta square by factorial 2 plus theta to the 4 by factorial 4, right. So, what we see this neglect the higher order term, but we just keep it but this is square. So, theta minus theta cube by 6, right, minus PL, this will go, and this is theta square by 2 minus to the 4 by something like that, right. Now, you see that. So, phi is a function of what? It become a function of theta square, see theta square plus theta to the 6, right, theta plus 2 theta theta cube, this, right. So, these are all, so here also it is a quartic term. So, theta square, theta to 4, theta 6, right, all are square, square term. So, like earlier, these are all what? It is always positive definite, right, potential energy functional, right. This phi always consists of, there is no odd term, all are even term, all even term, all even term. So, because all are even terms, right, that is why it leads to what? Symmetric bifurcation. Please note that. The difference with the previous system, where the rigid bar was restrained by the rotational spring, is that both lead to stable symmetric bifurcation, but one is stable, but this one is unstable. But in both the cases, the potential energy functional consists of term which are all appears in square, quartic and six, like this. Okay, clear? So, please note that because there is no odd term, that is why symmetry. Okay. So, if you draw the equilibrium path, if you draw the stability diagram, the way it will look like is theta, and then I am just right here, and then you see these are all unstable, and from there these are you see that. So, here is the critical load, this value is nothing but this value is K into L, okay, and after that this is, you see earlier it was concave surface, here it is convex, and this is, so all this dotted line is unstable, right, and this is stable. So, a stable fundamental path, that theta is equal to 0, bifurcate into an unstable fundamental path and an unstable post critical path, okay, right, fine. So, if you want me, I can just write it, so the way previously I have written, please, but you have noted that, right, the potential, be careful about the potential energy functional, okay. So, I will just write here, I am just removing these things, all of you have noted down, right. So, the stable fundamental path, that is theta is equal to 0, right, bifurcate into an unstable equilibrium path, which is corresponding to the straight configuration of the bar, which is corresponding to the state configuration of the bar and an unstable equilibrium path corresponding to the deflected instead of deflected you may use perturbed, okay, for the these are not deflector for the perturbed. Configuration of the bar. So, now we will clear. Now we have to study the imperfection sensitivity, right. So, what we have obtained. So, you are understanding that what bifurcation is. So, from here this is going, but at theta is equal to 0 when this load is reaching, it is unable to stay this in its equilibrium. So, in order to have an alternate equilibrium, it has to deflect, it has to have theta is the non-zero value of theta, right, and that path the equilibrium. So, this equilibrium path is unstable, right, fine, and so this is bifurcation because this path is followed and then here it is bifurcating into a different path, alternative path, right. So, that is why this bifurcation is happening, right, and it is symmetric with respect to this, and this is also associated with the symmetry breaking. Why symmetry breaking? Because what is happening, you see, until when the load is less than that, you take the bar and in perturb it. So, you give any perturbation like theta positive negative, it will remain its theta is equal to 0, right. So, it does not distinguish between theta is equal to 0 or theta positive or negative, right. So, that it was symmetric basically, right, with respect to its stability, right, it will bring back to it this, but as soon as this is reached, then it intend to diverge, it is unstable. So, when you are perturbing, it will what? It will diverge to any particle. If you are giving a positive perturbation, it will tend to diverge towards that. So, that means it is breaking it is losing its symmetric behavior with respect to its deflection. You see that? So, that is the notion of symmetry breaking. Although this is a more generalized term that is used in physics actually, physicists use this symmetry breaking, okay, for bifurcating system and others, but for elastic system stability this is also relevant, okay. So, now we are going to, so all of you have take a note of this, right. So, now we are going to consider the imperfection to see its imperfection behavior. So, quickly we will not, so the potential energy for the imperfection. So, when we are treating it to be imperfect, right. So, what we are assuming that initially there will be some deflection, right. This angle is alpha is the imperfection here, and then alpha is the magnitude of imperfection, right, imperfection. So, then potential energy, once again it is very simple, earlier whatever we have used. So, L, the deflection delta will be, the spring deflection will be what, L sin theta. So, L sin theta whatever earlier, but because of imperfection it was L sin alpha. So, it is L sin theta minus sin alpha, right, and the vertical deflection of under this P, right, that will be what, earlier it was L cosine of alpha minus, now it is L cosine of theta. So, L cosine of alpha minus cosine of theta, right, alpha is the imperfection, right. So, I am writing the expression. So, here half k L square sin theta minus sin alpha square minus P L cosine of alpha minus cosine of theta. So, I am not going to do the differences and all these things now. I will just write the expression just to all of you know how to do that, right? Fine, this was the only difference, right? On incorporation of the imperfection alpha. So, alpha is nothing but the initial perturbation, okay? So, then del pi del theta, I want to find out the equilibrium path. So, equilibrium path, how it is given? Equilibrium path will be CL cosine of theta 1 minus sine alpha sine theta. It is simple, if you just substitute you will get it, okay. This is the equilibrium path, okay. And from for the critical load del 2 pi del theta 2, so that is the critical load, right, critical load value of P. So, that you will see if you write, this will be P critical will be CL cosine of 2 theta plus sine alpha sine theta divided by cosine of theta. See, if you substitute alpha is equal to 0, then it will mimic the perfect system, right? And now, I am not doing the simple manipulation calculations, that you can do yourself, right? Now, what I will do for the critical, whatever del 2 pi del theta 2 got the equation, right? So, del 2 pi del theta 2 will essentially be, we will combine these two. See, what we are going to do del 2 pi del theta 2 will definitely we will get in terms of P, right? But then we must impose the equilibrium on that. So, then the way we did earlier, we will try to get the expression in terms of theta and alpha only, no P, right? Oh, sorry, it will be K, right? It's K, because it's the not rotational spring but translational spring, again the stiffness of the spring, okay? K is the stiffness. So, here this if you substitute, so the way you are doing, you are making it 0, then so you are double differentiating it and then you are substituting whatever the equilibrium path on that. So, combining you will see that simple expression I am going to get CL square KL square by sine theta and here sine alpha sine square theta minus sine, or it will can be further simplified. Let me write it down. It will be it will be KL square. So, KL square sine theta sine alpha minus sine cube theta, okay. This is the double. So, now you tell me, so what will be the, so stability condition is what? It is greater than 0, right? This for stability, right? For stability, this is the condition, right? And we want to find out the stability boundary now. So, stability boundary what? Where del boundary means when del 2 pi del theta to double derivative is going from positive to negative. Then we said 0, that means when it will. So, for stability boundary, sine alpha minus sine cube theta must be 0, and then from here we get some some critical value. So, sine cube theta critical is equal to sine alpha, okay. So, that basically gives us the stability boundary, okay. Now, of course, how will you do the path? Of course, we will take different value of theta and we will take little imperfections and we will plot there. So, if you plot that, the way you have learned earlier, this will be this will be the imperfect system will be asymptotic to this. So, let me see how it will look like. So, this is alpha greater than 0, alpha less than 0, alpha greater than 0, alpha less than 0. So, you see that. So, here this is the stability boundary, okay. This is the stability boundary. So, you see, I mean, you have all know by now that see why this is shifting, because see that this need to be positive, right. So, you can understand that for different value of alpha, the stability boundary will change, right. You see that. So, these are for increasing alpha, this is for increasing alpha, this is for increasing alpha, these are for increasing alpha, these are for increasing alpha. When I am putting this, so that means increasing alpha, in increasing alpha, imperfection. You see this little flowery structure, another thing. So, please draw this figure first. Now, so you understand this diagram. So, from here you can clearly see that, see del 2 pi, so Hessian positive also implies that del p del theta is also positive, del p equilibrium by del p is also positive, right, because Hessian it is equivalent to be the tangent stiffness, right. So, you see that here if you take this, slope is positive until this, here also negative, slope is negative. So, essentially this is positive, okay, del p del theta. So, that is what until this is positive, after that this is being negative del p del theta, that is what this is unstable, clear, and it depends very much on the imperfection magnitude alpha, okay. Now, we will see the imperfection sensitivity. How will you do that? The way we did previously. So, earlier we directly attacked this P critical, right, P critical, and then we made that we have from stability boundary, how we have reached at the imperfection sensitivity. We consider the stability boundary and thereby we eliminate everything. We have related this for theta with alpha, for some theta stability boundary, that basically related the theta with alpha, okay. That means where the alpha plays a critical load in terms of changing the stability boundary, okay. So, that we have identified, we substitute that value in P critical, that is the way we find it out, right, in previous example. Here what we will do, that we can also do the same thing, but we can also, and in the previous example where it was stable post critical path, we have seen that it follows to the power law, but critical load increases with the increasing imperfection. There is another format to the imperfection sensitivity that directly start with the equilibrium path itself. So, instead of many substitute here, I am going to substitute this here, okay, and you will see I will bring in a different. You understand that P KL is nothing but P critical. Critical means that theta is equal to 0, right? Okay. So, P is equal to KL to sine of theta 1 minus sine alpha by sine theta, right? And what we have seen, sine theta is equal to sine of, sine cube theta is equal to sine alpha. We want to relate P in terms of alpha, right? And what I know, KL is critical. So, P, you please see, P is equal to P critical cos theta 1 minus sine alpha by sine theta, fine. Now, so P by P critical is, now in stability boundary I can see sine cube theta is equal to sine alpha, right. So, I will substitute here. So, cos theta is nothing but 1 minus sine square theta half and then 1 minus sine alpha by sine theta, this, okay. So, P by P critical is equal to 1 minus sine, so sine square theta will be what? Nothing but sine alpha 2 by 3 half and then 1 minus sin alpha. What is sin theta? Sin theta is sin alpha 1 by 3, right? Here 1 minus sin of 1 minus sin one minus so minus 2 by 3, right, alpha. Okay, and then what I will do, I will just now we will do for 1 minus oh, this is sin 2 by 3, yes, yes. So what, okay, so what we can do, 1 minus sin alpha 2 by 3 and then here it is half and half. So this is 1 plus half means 3 by 2, right. So then I will just further simplify it from here. Let us come here. So P by P critical will be here, if you take binomial, 1 minus 3 by 2 sin alpha 2 by 3 and 1 minus 3 by 2. We can assume sin alpha to be alpha if alpha is small, right. So alpha 2 by 3. So what we see that P by P critical can be approximated 1 minus some constant, C, maybe alpha to the power 2 by 3. So what we see that as imperfection will increase, the load carrying capacity will decrease. 1 minus 2/3 power law is coming. Do you see that? So this says that it follows 2/3 power law of imperfection sensitivity It follows 2/3 power law of imperfection sensitivity, and it is imperfect, and it is mild imperfection sensitivity, mildly. I will explain to you why it is mild. Okay, it is mildly imperfection sensitive. Why it is mildly, that I will explain to you. The previous example, P critical was 1 plus, that means with imperfection critical load was increasing, but here it will be decreasing, load carrying capacity will decrease. So that is what earlier one, it was not imperfection sensitive, but this is imperfection sensitive, okay, and it is decreasing. So we will also draw the imperfection sensitivity diagram. So imperfection sensitivity diagram will look like alpha here and here P by P critical, and this is P critical. I mean this value is 1, maybe we can put it 1, this is 1, right, and this is decreasing, right, imperfection sensitivity diagram, right. The previous one, how it was looking like? It was from here, it was what? Like this. It was going up, right? From there it was like this. If you could recall earlier one, it was like this, for the stable bifurcation, post-critical bifurcation. But here it is going down. Fine? Okay. And what is this two-third part law? I told you, who has mentioned that of course the way we are doing is little ad hoc by using very simple system, toy system, and with simple expression, simple energy, potential energy functional, but this there was a rigorous derivation by von Karman, right? Quieter, sorry, quieter, right? Quieter's imperfection sensitivity, quieter, okay. So, we have learned the second system and its behavior. What kind of system will show this kind of behavior? Can you associate it physically? So, load, it will be mildly imperfection sensitive, okay. So, some of the see previous example where it was imperfection insensitive and the stable post critical bifurcation, this kind of behavior was portrayed by this kind of behavior is portrayed by column undergoing large deformation, buckling of column, buckle column or even buckle plate as well. And here where it is the unstable post critical path, this is demonstrated by some of the buckling mode, okay. Buckling mode means this is single equilibrium system, right. So, you will see that when you will study the cell buckling, buckling will have multiple mode and some of these mode are very closely spaced. So, it will have symmetric mode, it will have anti-symmetric mode. So, some of the buckling mode there, especially the one which are symmetric, those mode will be mild imperfection sensitive, okay, where the load will drop with increasing imperfection, okay. Various mode will show different, but some of the symmetric mode may show this kind of behavior in cell buckling, okay. So, that is the physical example, which you can equilibrium path you can mimic here, through finite element analysis. What you have also understood that when you are incorporating imperfection, the bifurcation is disturbed, right. It is asymptotically approaching towards the towards the bifurcation behavior, right, to the bifurcating path and thing, but on incorporation of the imperfection, the path is basically devoid of any bifurcation. It's a different path it is showing, right. However, it is asymptotic to the bifurcating path, right, fundamental, the imperfect system, clear. Okay. So, now we are going to consider a third category of system which will show you both these systems we have discussed are symmetric bifurcation, they give symmetric bifurcation. Now, we will consider asymmetric bifurcation. So, please recall that for the symmetric bifurcation, both are symmetric bifurcation, but in one case it is stable post critical path, whether in other case it is unstable post critical path. In one case, at critical load, the equilibrium is stable, whether the other one at equilibrium the critical equilibrium at critical, that is unstable, and that cannot be captured using just Hessian, but you have to explore the higher order derivative. Now, on incorporation of the imperfections, we have seen that they show one of the system does not show imperfection sensitivity, whereas the other shows imperfection sensitivity. Both follows two-third power law of imperfection sensitivity, okay, which are mildly imperfection sensitive. So, you will see that whenever the post critical path is unstable, it will be imperfection sensitive. So, it is a general conclusion. Okay. So, now we will go for asymmetric bifurcation. Asymmetric bifurcation, and there, because it is asymmetric, so both the stable as unstable post, both stable and unstable post critical path. Stable, unstable, both stable and unstable. So, it shows the same behavior, same system, because it is asymmetric, it shows both the stable as well as unstable behavior. Okay. So, this that there is a saying, right, like multiple behavior in the same system. Okay. So, for that we are going to consider a system, and now I am not going to consider the I am not going to consider the perfect system. Okay. I am going to consider the imperfect system directly, and from there we will specialize for the perfect system. Okay. So, here you see that once again there is a rigid bar, and this bar is of course subjected to a P load, and then from here it is restrained by a spring, but that spring is inclined, translational spring, inclined, and this you can understand that you have to have a roller support on the inclined plane. Okay. And then this angle we will put this angle to be 45 degree. Okay. For simplification. Okay. This is 45 degree, this angle. Pi by 4. That means pi by 4. This is length L. So, if this is L, then this length is also L, if it is 45 degree, and then this length is L root 2, right. From here to here, this length is nothing but L root 2. This is the hypotenuse for the right angle triangle, right. So, we are assuming initially. So, we are going to perturb the system. For the first lesson stability class is that we have to perturb the system. So, I am perturbing it. Okay. So, when I am perturbing it, it is reaching to this configuration. I assume that reaching to this configuration, and then this is this here. Okay. So, we are assuming that initially maybe there is some imperfection, this imperfection is alpha, and then after that there is theta, initial imperfection is alpha, and then the perturbation is theta. Okay. So, you can understand. So, the way we are going to consider the we have to assess the potential energy function, right. So, potential strain energy balance work done. So, for the you can understand that the way you will this is very simple, because this is earlier it was L, if you consider this deflection, this is under P, right. Deflection is will be nothing but L cosine of alpha minus L cosine of theta, right. So, L cos alpha cos theta under P, right. But what about the spring? The displacement in the spring will be what? So, the way we are going to do is we are considering this length is L, and from here we are going to draw perpendicular this angle. Okay, perpendicular. So, if this length is L, this is L, right. This is L. Then what about this? L cosine of, see, if this angle is alpha, then this angle is what? This is nothing but pi by 4 minus alpha, right. So, this one is L cosine of pi by 4 minus alpha, and 2L 2L pi by 4 minus alpha, 2 L into cosine of pi by 4 minus alpha, and then so this is for alpha, and then when it is theta, then same 2L cosine of pi by 4 minus theta. Okay. So, ultimately the expression, the elongation is spring will be L cosine of 45 degree, 45 means pi by 4, pi by 4 minus theta minus cosine of pi by 4 minus alpha. Okay. Understand, right? All of you understood, right? Why it is so? Huh? Because we are doing dropping a perpendicular from this point to here, and then this, if this angle is alpha, then alpha cosine of this angle is nothing but pi by 4 minus alpha. So 2 times of this. Okay, that's what here. So potential energy function phi is strain energy minus work done. So half k L square, cosine of pi by 4 minus theta minus cosine of pi by 4 minus alpha square minus EL cosine of alpha minus cosine of theta. So let us do differentiate phi theta is equal to 0. Differentiating I will just write it, okay. Simplified expression. So del pi del theta will be equilibrium path will be P will be AL, and here it will be sin theta, and here it will be half cosine of 2 theta minus sine of pi by 4 minus theta cosine of pi by 4 minus alpha. This is the equilibrium path. This is the equilibrium path. Second, we could have, so I will write another version of P, okay. So you have noted these things, right? Okay. So this is little involved to simplify, but we will do that, okay. And we will also make use of the relationship that del 2 pi del theta 2 del 2 pi del theta 2 is equivalent to del p del theta equilibrium, okay. That's what we will make here. Huh? So the equilibrium path is P is, this is k L y sin theta half cosine of 2 theta minus sine of pi by 4 minus cosine of and we will directly simplify this, okay, by series expansion. So for that I am just you can do yourself, sin pi by 4 minus, the way I am doing simplification, you please note it. So sin A minus B, sin A cos B minus cos A sin B, sin 45 degree or sin pi by 4 is nothing 1 by root 2, right. So if you just write 1 by root 2 cosine of theta minus 1 by root 2 sin theta, and then it is 1 by root 2 cosine of theta 1 minus theta square by factorial 2 other things minus 1 by root 2 theta minus theta cube upon 3. Why I am doing this thing, it will be clear to you, because this is a asymmetric system. Why it is asymmetric? Because you see, when you are pulling it apart, right, see, this is the restoring force. So the destabilizing force is nothing but P L sin theta, this is the, right. The restoring force will be nothing but this restoring force multiply moment with respect to this will be, this is the nothing but the lever arm, right. But then when you are perturbing it in clockwise, then with increasing theta, this this distances are decreasing, whereas when you are taking it to anti-clockwise theta, then this distance is increasing. That means the stabilizing force is varying with positive or negative theta. You understand? So, because stabilizing force, so that is what this kind of system is chosen. Angle 45 degrees just for simplifying the calculation, but this inclination is because of that. We want to make a system in which the system will distinguishes between the positive theta and negative theta, and the way it is distinguishing is that it is basically in one direction it is the restoring force is increasing, in another direction it is restoring force is decreasing, whereas the destabilizing moment is not basically changing, whether it is this and this, it does not really matter. That is why in one case it will show stable behavior, post critical stable behavior, whether in other case it will post critical unstable behavior. When it will be stable, when the restoring force, restoring moment will be dominating over the destabilizing moment, then that time it will be stable. The unstable will be opposite and that will be reflected, but we are not considering directly the equilibrium or that kind of notion, rather we want to have more objective assessment, and that is what we are trying to use our energy concept. Clear? But ultimately what is happening, that you must see that. And there is another important difference that we are going to anticipate. See, in all the previous system where it is showing symmetric bifurcation, okay, stable, unstable, whatever, our potential energy functional consisting of all square term, quartic term, or sixth, eighth, this kind of even term, right, even power. Here, because of this asymmetry, it has to distinguish this asymmetry. How that is possible? It will include the odd term, not only even power. So that is what we want to see here. And because of this odd term, it will show interesting behavior, and you will see it will show the notorious imperfection sensitivity, half power sensitivity. All these things we are going to explore, and that for that, instead of trigonometric function, we are going to do polynomial function. So I am not always doing I am continuing with the trigonometric manipulation with trigonometric function. But one thing I can suggest to exam and wherever try to simplify this trigonometric in terms of polynomial by series expansion. That largely simplify the problem. Not only that give you intuitive kind of notions about the stability behavior of the system. Clear? So this, if you I am just and you do not require to retain all the term. You just retain this term, first two term. Okay. So you will see that it is 1 by root 2, 1 minus theta square by 2. Okay. Similarly, cosine of y by 4 minus alpha will look like 1 by root 2, 1 plus alpha minus alpha square by 2, alpha cube by 6. Although we are not going to consider all the term, only square term we will keep. Okay. But please note this thing. Okay. Please note. And we will simplify cos 2 theta. Cos 2 theta, it is this term. This term is like simplify like that. This term simplifies like that. Although we are not going to consider the, we will retain until cube term. Okay. So cos 2 theta, 1 minus 2 cos square theta, and 1 minus 2 cos square theta, 1 minus theta 1 square by factorial 2. All terms we are not doing because we have to take square root. Ultimately, you will see 1 minus 2 theta square, right. So if you substitute everything, and sin theta means theta, sin theta, the expansion is what? Sin theta is what? Theta minus theta cube by 3, right. Factorial 3 plus theta to the power 5 by factorial 5. We are not going to consider this, so we are going to consider theta minus theta cube by 6. Okay. And we will just take it further. So all of you please note these things. Okay. otherwise maybe later it will find it difficult to simplify. Clear? Please note it down. You have already noted this too, now note this. So, 1 by sin theta, we are approximating as 1 divided by theta minus theta cube by factorial 3, and then this being theta minus theta cube by 6 inverse, and then that means 1 by theta, 1 minus theta square by 6 inverse, and 1 by theta 1 plus theta square by 6, and then 1 by theta plus theta by 6. So, P critic. So, what we are going to do, P we are going to write as CL, that is the equilibrium path. This P is the equilibrium path. Please note that this will be KL, on substituting all these polynomial expansion, we are going to get KL by 4 1 by theta plus theta by 6 here, and then here 2 theta minus 2 alpha minus 3 theta square plus alpha square plus 2 theta alpha, and P is equal to KL upon 2 1 minus 3 theta by 2 minus alpha by theta. See, this is the equilibrium path. Ultimately, doing all these things, see, we are simplifying this. You see, trigonometric terms, it is much easier to deal with this, of course, higher order terms we neglected, but there itself we will be able to do lots of stuff, okay. And what you can clearly see that you want to equilibrium path, and if you take double derivative, del p del theta if you do, so del p del theta, what will it come? Some of the higher order terms we are neglecting. What rewriting is KL for 2 1 minus 3 minus. So, dp d theta is what? dp d theta, neglect this minus, theta is equal to 0, we are going to minus, it will be minus alpha theta square, and then for very small theta we can neglect this thing, right. So, it will be minus 3 you see, okay. So, from here I will just find out the dp d theta will be is equal to, so I will make it dp d theta is dp d theta is KL by 2 minus 3 by 2 minus alpha by theta square, so plus, okay. So, if I make it 0, so from here you will get 3 by 2 is equal to alpha by theta square, or theta is equal to 2 alpha by 3 half, right. Then I will just write P is equal to KL by 2 1 minus 3 by 2, this theta I will substitute here, 2 alpha by 3 to the power half, okay, minus alpha 1 by theta means 2 alpha by 3, 1 by theta means it will be minus half, you see that. So, you see that this we can approximate it, KL by 2. So, Of course, this term will be dominating over this term because alpha is small, right. So, you will take square root, okay. You see that. So, I can write 1 minus 3 by 2, you know, whatever 2 by 3, whatever half is there, alpha to the power half, okay. And so, ultimately, see if you do this, you know, this KL by 2, okay, that KL by 2 is nothing but that that is the critical load for this case, okay. If you perfect system, if you study that KL by 2 is nothing but the critical load, okay. That I have not demonstrated, but that you can do, okay. KL by 2, this KL by 2, okay, this one, this one, So, you know, this P. So, from here I am just removing this, please note that. This condition we have obtained from the transition, that means the stability transition, right. So, where we can see P is equal to P critical is nothing but KL by 2. KL by 2, this is the basically critical load, that means where the bifurcation is occurring in the perfect system, okay. That I have not demonstrated, but if you for perfect system, if you do, you will put the alpha is equal to 0, that is what you will get KL by 2, okay. You put theta is equal to 0, okay, theta is equal to 0, alpha is equal to 0, then you can see P is equal to KL by 2, you see that, okay. So, critical load will be KL by 2, So, P is equal to P critical 1 minus some constant, maybe here is some constant, maybe I am C cap alpha to the power half, right, or I can write P by P critical is equal to 1 minus C cap alpha to the power half. What do you see? Half power imperfection sensitivity, half power imperfection sensitivity, imperfection sensitivity. That is called extreme imperfection sensitivity. Extreme imperfection sensitivity. So, I will put here P critical KL by 2. So, now I am removing all these things, all of you have noted down, must have noted down this, and what I am going to write here is, I will draw now. So, P critical was nothing but KL upon 2, imperfection sensitivity I have say half power. So, I will draw it, and I have also shown the equilibrium path to be, that I have also that was nothing but KL by 2 1 minus 3 theta by 2 minus alpha by theta, that was the equilibrium path, and I will also write the potential energy expression, okay. Time is there, no? I will write down the potential energy expression. That potential energy expression will be potential energy expression pi will be KL square by 4. In fact, we have neglected many, some higher order term here, because it is in terms of P, but if you take the port energy, then it will be square. So, I will write it, reasonably, with reasonable approximation, okay. All these terms are not required, but then I am writing for your understanding, okay. What do you see here? That you see that theta square alpha square by theta cube. Do you see that cubic term, which is cubic term, the potential energy, which is asymmetric, right? Cubic is not symmetric, right? Alpha square theta square alpha, alpha theta, theta alpha square. This is asymmetric, this is also asymmetric term, and alpha theta square is symmetric, but alpha this is asymmetric. Theta alpha is also similar and alpha cube. You see that symmetry asymmetry. So, it is a it is not that it in all these two previous example where it was symmetric bifurcation, the potential energy functional content term which were all in even power, but here these are a odd power and symmetry asymmetric terms are populated all over. Clear? I am going to draw this now. What how then stability diagram. So, please note that, please note carefully. Oh, this was the perfect system, this was the perfect system, okay. And this is the stability boundary. Okay. So, you see that please that this is the this value, this corresponds to this value corresponds to nothing, KL by 2, okay, which is critical KL by 2, that is basically peak critical, okay. So, do you understand the bifurcation? So, once again, this stable fundamental path is going, please draw it and then I am going to explain to you. We will just finish with that. So, let me explain to you. This is the imperfect stability diagram. You see that asymmetry is clear here. You see that when this is alpha positive, this is this is theta. So, theta positive, theta negative. This is negative theta. Okay. So, when theta is negative, the critical load is increasing. You see that here the value is KL by 2, but there it will increase because theta negative, negative it will be positive. But here you see that because this is odd term, right? And similarly, I am neglecting, but cubic term will also be there. Okay. Similarly, in the denominator there is also another term. So, on the right hand side, left side this is increasing, right hand this is decreasing, and here at this when the bifurcation is occurring, perfect system which is scale by 2. So, stable fundamental path is going and bifurcating into an asymmetric path, and then fundamental path is being unstable, right. So, the perfect system. For the imperfection system, what is happening? For different imperfection alpha greater than 0, less than 0, there are 4 quadrants, right. Here you see this is once again asymptote. See this path, the stable path is asymptote to the fundamental path, whether the unstable part is asymptote to the post critical path. See that imperfect system, and these are all increasing imperfection, these are all increasing imperfection, these are all increasing imperfection, these are all increasing imperfection. Please note that. You see that? So, imperfect system, the equilibrium path, it is asymptote to the fundamental path, and another limb it is asymptote to the post critical path, stable. Here it is stable, here it is unstable, and I explain what is happening, why that side is stable, because the restoring force will have a higher moment arm, okay, that is what it is resulting in much larger restoring moment comparing the destabilizing force, which is not changing. Whether in other case it is not, it is being dominated by the destabilizing forces, okay. And there you see another important thing, that here you see this positive slope, here negative slope. So, essentially tangent stiffness del P del theta is being positive, right. So, and then the stable to unstable transition is given by this line. You see that here it is positive slope, but here it is negative slope. This is the line, and this line, please note that this line is basically bifurcate. This is a bisector of this angle. This stability boundary is nothing but a bisector of this angle. Bisector of this angle. Clear? Okay. Now, having said that, let us come to the imperfection sensitivity diagram. What is happening? It is half power sensitivity. So, when you are taking square root, it cannot be negative value of alpha, it is said to be positive value. So, I am just putting only positive value of alpha, only positive value of alpha, alpha is positive. And when I am taking the root, there will be 2 root, one root is extraneous, only the less root, 1 minus root. So, this you see that P critical, upper one I am not taking, the lower one, this it is diminishing very fast, very fast. See, if you take alpha is a much less number than 1, right. So, what will be less, 2/3 or half? Which one will be less? Well, which one will be more? Half will be more, right, rather than 2/3. So, that means 1 minus alpha half, right. So, that will be more. So, that is what you see, if the 0.001 imperfection, that is 7.8% decrease in critical load, with the 0.01 in 24% decrease in critical load. So, this is extreme level of imperfection sensitivity, and that is what you can clearly see that, right. Clearly see this one, this one corresponds to the first one, this one corresponds to the second one. So, this is the imperfection sensitivity. So, half power sensitivity is extreme level imperfection sensitivity. Now, what I mentioned to you earlier, that which structure will portray this kind of behavior? Analogous elastic system, elastic cell buckling will portray this behavior. There will be symmetric mode, there will be asymmetric mode. I will show you at the end of this course. Okay. Now, asymmetric mode will show this kind of behavior, extreme level of imperfection sensitivity. Not only that, there are additional things that happen. Okay. 2 mode can interact, and apparently that interaction we are going to demonstrate to you. So, individual mode might not be imperfect sensitive, but due to interaction, modal interaction, there can be imperfect sensitivity imparted. Okay. So, this is the third system. So, I am not writing the behavior, but what happened? a stable fundamental path bifurcate into a unstable and stable asymmetric path, right, and a unstable fundamental path, right, and the system become imperfection sensitive, extreme level of imperfection sensitive. On incorporation of the imperfection, the bifurcation structure breaks and then symmetry breaking, there is symmetry breaking occurs, right, and then for the imperfection system, the equilibrium path asymptotically approaches the perfect system. Coming. Thank you. Okay. Thank you for today's.